Hello everyone. Today I'm going to solve one example of this Fourier analysis of stability, and then we will look at stability versus accuracy. And I'm going to solve one example of that as well. So let's get started. Example. Classic explicit finite difference approximation, and I want to find a stability criteria for that. Okay, so uj n plus 1 equals to dimensionless diffusion parameter uj minus 1 at time n plus 1 minus 2 d uj n plus d uj plus 1 n. The same equation we had before here. I want to show this stability criteria using this Fourier analysis. Okay, so this was something we just mentioned without any proof, but now I want to find it here. So uj n is u at xj and tn, correct? Which equals to u j delta x and n delta t. And for arbitrary wave number sigma k, this will be what? From this equation I can just write lambda k power n plus 1 times ck e I sigma k j delta x equals to, so this is from here, right, the initial conditions that we have, and then lambda k is what we defined, right? What we defined there is lambda k. Lambda k is the amplification factor that we defined here, right? So now I want to substitute those definitions here. So this equals to d lambda k to power n ck. The first term is going to be ei sigma k j minus 1 delta x plus 1 minus 2d lambda k to power n ck e I sigma k, and I is here the imaginary I, j delta x plus the last term, which is going to be d lambda k to power n e I sigma k j plus 1 delta x, right? So this is exactly this equation which I wrote it based on these Fourier terms, okay? So the next thing we want to do is divide everything by lambda k to power n times ck EI sigma k j delta x. And let's see what we will get from that equation. The first term, the only thing that remains is lambda k, right? On the right hand side, the first term is going to be d e minus I sigma k delta x plus 1 minus 2d plus the third term is going to be d ei sigma k delta x. Okay, so this is what we get when we divide that equation by lambda k to power n ck ei sigma k j delta x. And now I want to further simplify this to get a criteria for lambda k. This criteria, I want to see what that would be and what that would entail. So let's see. Lambda k equals to 1 minus 2d plus d, I factor d, ei sigma k delta x plus e to the power minus I sigma k delta x. Okay, and these two terms, based on their definitions of ei to the power theta, which is an imaginary number here, and you can see it here based on this definition, we can write it as 2 cosine, if you write it down, you will get 2 cosine sigma k delta x. And therefore, I am left with minus 1 minus 2d plus 2 d cosine sigma k delta x. And this equals to 1 minus 2d 1 minus cosine sigma k delta x. And based on some trigonometric relations, you can write this as 2 sine square sigma k delta x over 2. Okay. And therefore, lambda k equals to 1 minus 4d sine square sigma k delta x over 2. And for stability, we require lambda k, the magnitude of that, to be smaller or equal to 1. And this means that it should be between minus 1. So 1 minus 4d sine square sigma k delta x over 2 and 1. So the right condition means that 4d sine square sigma k delta x over 2 should be always greater than or equal to 0, which it is. So always okay. But the left one entails 4d sine square sigma k delta x over 2 should be smaller or equal to 2. And this means that d, dimensionless d, should be smaller or equal to 1 over 2 sine square sigma k delta x over 2. And the most restrictive case is when sine square sigma k delta x over 2 equals to 1. So the most restrictive case tells us that d should be smaller or equal to 1/2. And this is what I already wrote before, right? Without proving that. This is the thing that we had here without any proof. But this is a formal proof of that and the formal stability criteria for that. So this is the stability limit. Okay. So this was one example of how we can use this Fourier stability analysis to approximate and find the stability criteria of any finite difference approximation. So this is how you should approach it. That is, you assume this as the initial condition, you put that into the original equation, and at time tn is going to be something like this, and you just propagate it in time, find an equation, stability equation, and require this condition for lambda k. And based on that, you can find the stability limit of your problem. Okay. So now I want to investigate accuracy versus stability. So far we only talked about stability, but how about accuracy? We talked about stability criteria of these numerical methods. But I want to now introduce a way that you can also investigate the accuracy of these methods by the same analysis, which is Fourier analysis. So to do so, we also do the Fourier approximation. So the analytical behavior. And the reason we need the analytical behavior of the solution is that now I want to find accuracy, and in order to find the accuracy of any numerical method, we should compare that with the analytical solution of that method. Okay, so the analytical behavior of the solution can be approximated also using this Fourier analysis, and to do so we assume, or we allow u, x, and t, which is the analytical solution, to be shown as a sigma k, a Fourier series of omega kt ei sigma k x. Okay. So for example, for this diffusion equation, partial u over partial t minus d partial square u over partial x square equals to 0. We can write in terms of this series, Fourier series, as sigma k of the first term is a partial derivative in time for this, so it's gonna be the only thing in time, a function of time, is this omega k. So I'm gonna have d omega k over dt, and the other terms are constant, so I just write it ei sigma kx minus, and then the second term is partial derivative with respect to x, and this is going to be constant because it's only a function of time and I only need to account for this. So it's going to be I sigma k square, which is going to give me, so d the first term is constant sigma k, omega k, and then I have I sigma square, I sigma k square. I square is going to be -1, so I just write -1 times sigma k square ei sigma k x. Okay, so this gives me sigma k d omega k over dt plus I factor ei sigma k x plus d sigma k square omega k ei sigma k x equals to 0. And in order for this to be 0, for all k's, we need this to be 0 because this is not going to be 0, right? This is not 0. So if this is 0, then for all k's, then this is going to be valid. So let's see. One of the solutions is going to be d sigma k over dt plus d sigma k square omega k equals to 0. So this is a simple first order ODE. So we can simply solve that. Omega kt is gonna be alpha k e to the minus d sigma k square t. By simple integration, you can solve it. And we know omega k at time 0, which is the initial condition, is what? If you look at here, based on the definitions that we had, we represent it as ck, right? At the initial condition. So the same thing here, I'm going to use the same thing here for initial time. So it's going to be, it should be ck. Okay, so alpha k equals to ck, right? Because at time 0, this is going to be 1, and these two should be equal, so alpha k should equal to ck. And therefore, omega k t equals to ck e to the minus d sigma omega sigma k squared t, and u x and t equals to sigma k ck e to the minus d sigma k square t times e to the I sigma k x, right? This is based on this definition here. So these are our findings, and the next step that I'm going to do is to use these for defining a numerical analytical amplification factor. Okay, after this, that now we have defined this based on Fourier series analysis, similar to the numerical amplification factor, I'm going to define an analytical amplification factor.